Click the bell icon to get latest videos from Ekeeda.
Hello friends, welcome back to the subject of Machine Design 1. We are right now learning about design of various springs. In the last lecture, we have seen the introduction regarding helical springs and their lip springs. Today, we are going to look at the design aspects of helical springs, and then we will continue with the numerical based on the design of helical springs. So let us begin. So students, we need to understand the design aspects of helical springs because it's a complex structure. Like we have mentioned this in the previous lecture also. Now why it is compressed or why the structure is complex. If you see this properly, a spring, if you can imagine right now, is a structure made up of different wires or one wire which has got a coil structure. But that's not a simple coil again. It got certain angle also, and that's called helix angle. So the complexity are many in nature. If you see this properly, not only a bar, or we can say if this is the bar which is the wire, we have to bend it in coil manner. So, and that's called spiral, of course. The second thing is it will have certain angle at which it is a spiral, so that's why it is a helix angle. So the basic structure, which was a simple bar, is now converted into a complex structure where the nature of forces acting will vary. And since the structure is complex, we have to analyze it using maximum possible aspects. So let us look at them. Basically, there are two aspects which I used and which have proven very strong for the design of springs. The first aspect is called load stress equation and second is called load deflection equation. So based on these two aspects, we can design the spring or the helical spring. You see, this load stress equation is based on the modified bar. Like I said, if there is a spring given of certain number of coils, let me unwind these coils, let me make them straight. So this straight things will take a form of bar of certain length. Now this bar and this spring will have only one thing that is in common, is the cross section, small diameter d, whereas the total length of this modified bar will be equal to the circumference of one coil into number of coils. So in that case, this is how the simplified bar is or the modified bar is. Now this particular spring is now converted into bar and then it is analyzed for various stresses. Let's look at them. The possible stresses that are possible, or the possible stresses that are causing the failure, that may cause the failure in a spring, are pure torsional stresses, then direct shear stresses, then comes the combined torsional stresses where the torsion and other direct stresses will be combined, and the last one is the curvature shear stress. Curvature is nothing but this curve portion which may undergo or which may experience the shear. So these are the possible four types of stresses that will induce in a spring which is actually a simple member. And that's why we need to analyze using all of them. Now since the derivation is not a part of our syllabus, we are going to look at it very quickly. The stresses are combined in the form of this particular formula where shear stress is prominent one. If you see torsion, shear and torsion, and that's why everywhere the stress that is occurring is the shear stress, and that's why the shear strength of this particular member will be given by this particular formula, where there are certain terminologies we need to understand. This is a constant of equality, let's call it K for time being, into 8. P is the maximum force acting on the spring. It can be a compressive force or it can be a tensile force. D is the mean diameter of the spring and small d is the diameter of wire. So using this particular formula where all these forms of stresses are combined, we can do the design of the spring, where K is a constant of proportionality and it is called Wahl's factor. The Wahl's factor is given by this empirical relation. You can by heart it or you will find this formula in the spring section of your PhD data book. So this is the formula. Now if you recollect from the previous chapter, C is nothing but the spring index, and that is nothing but the ratio of the mean diameter capital D to the wire diameter small d. So using this empirical relation and this particular empirical relation, we can always find out the maximum stress that is induced in the body, or if the material is given based on the maximum allowable stress, we can always find out the wire diameter. Let's move ahead with the second approach. Yeah, basically this equation is called load stress equation, where load and the possible stress are equated in the form of, or they are put into one format which is called an empirical relation. Let's go to the load deflection equation. Now if you see properly, again, since it's a spring, it will have certain angular deflection. Now angular deflection is given by this particular formula, which is called a torsional formula. But now in that case, the maximum deflection, which is going to be the linear one, if we have to relate them, they have found out for very small angle theta, the formula is this. Of course, it's not a part of the syllabus. We are not going into the in-depth derivation of this particular relation, but we can call it an empirical relation, where the linear deflection is connected with the angular deflection theta, or twist angle you can say, by means of mean diameter divided by 2. Now in such case, when this particular formula was modified in terms of the torsion, it was found that delta is equal to this particular relation, where P is again the force acting, D is the nominal diameter or the mean diameter, and this n, or we can use small n in this case, which is nothing but the number of coils of the spring given. G is the torsional rigidity or constant of rigidity, and D is again the wire diameter. Now there was another relation found, was a small k factor. Now this k and this k are different. If you see, it's a capital K and it's a small k. So small k is given by the ratio of force to the deflection, which is nothing but the spring constant. It gives the unit Newton per millimeter. So it's the spring constant. So spring constant can be modified after using these two terms, P and delta. We will get the formula for spring factor is this one. So these two equations are called load deflection equation, whereas this particular equation is called load stress equation. Now a further analysis of this particular spring will be based on these two equations. Now students, before we move to the actual design procedure, we need to understand the material that can be used for springs. Now there are certain properties which are expected from the materials or the springs that are going to undergo certain environment. For example, the materials that are chosen for the springs based on the loads acting. The load can be compressive, it can be tensile, or it can be torsion in nature, and accordingly spring material will be defined and designed. For example, for the compressive strength or the compressive kind of spring, the material used will be different than the material used for the tensile kind of spring or the application. So load can be compressive or can be tensile or can be torsional also. The next thing is the range of stresses. Now students, like we have seen in the load stress equation, we have considered 4 different kind of stresses which are possible, which may fail this spring. So we always have to consider the range of or the ranges of the springs or the stresses which may occur. If there are only 2 stresses possible, we have to design and select the material only for those 2 stresses. If you are doing it for all other stresses, in that case the design will be over designed, right? So according to the stresses or the range of stress, we need to consider the materials. Then size constraints. Now students, spring is a small member that is generally fitted in multiple sections of a machine. So in that case, it always have a constraint related with the dimension, maybe length, maybe diameter, maybe the wire diameter available. So with respect to all these constraints, we have to select a proper material. For example, if there is a heavy application where the space for spring is very small, in that case we have to use a strength material or very strong material for the small application also. The next is fatigue like expected. Now springs are mainly used, or many a times they use in certain applications where cyclic loads come into picture. Also, they are dynamic in nature. Due to this variability, the spring member or other members, but we are concerned about the spring may undergo the fatigue failure. So there is some life expectancy and or the life expected by the manufacturer for that particular machine. In such case, depending upon the life expected, we should use a proper material which will have a more, or which will have a better endurance life or endurance limit. The next important thing is the possibilities of temperature and corrosion. Now springs are used in certain environment where corrosion or the liquid may come into contact with this particular spring. In such cases, we must consider the aspects of temperature as well as the corrosion also, because accordingly we'll have to select the material. So these are some of the important aspects that we must consider. There comes the different types of the materials. I'm not talking about the names of materials, different types of the materials, where the material can be a cold drawn springs. The cold drawn springs are generally used where the orientation of crystals are changed so as to suit the requirement of the given conditions. Then oil hardened steel wires. Now we know that these springs are made up of wires. The steel wires which may undergo oil hardening so as to suit the given environment. There comes the stainless steel springs. Many kind of applications where corrosion is possible, we may have to use stainless steel springs. And there comes another format where alloyed steels or alloyed wires are used for making these springs. For example, if there is an application where the conventional material like spring is like steel is not possible, in that case we may have to go for a higher end where the combined properties of different metals can be used, which are called our alloyed wires. So alloyed wires can also be used for making these springs. Now let us look at some of the most famous materials which are used. Now the names of materials which are used for making these springs. The very first one, and which is very prominently used, is called high speed or high carbon steel, where the carbon percentage is quite high. Now we know that springs are used for absorbing shocks. So castings or the material where the carbon content is more, they have got good capacity or capability of absorbing the shocks, and that's why we may go for the high carbon steel. The next one is the chromium vanadium steel. Chromium vanadium steel is a kind of alloyed wire which can be used for making the springs for special applications. Then comes the chromium silicon steel. It also is an alloyed steel where or which can be used for specific applications. Then stainless steel for corrosion material or corrosion environment we can use. And there are few more materials like monel, then phosphorus bronze, then bronze, silicon bronze, etc., which are again alloys or non-ferrous materials which can be used for making springs for given certain applications, specified applications. So these are what the important materials that we can use for the springs. Now let us move at the main part that is called the design aspect. Like we have discussed this, that the load stress equation is a prominent one, whereas the design of spring is concerned. Let us look at it. Torsion is main form of the load that act on springs, and that's why shear stress is the prominent one where the spring safety is concerned. In that case, we already know about the formula that is given by the induced stress is given by Wahl's factor, which is K, into this particular empirical relation where applied load, the nominal or the mean diameter of the spring coil, and the diameter of wire coil is used. Using this empirical relation, let me recollect that either we can find out the diameter of the spring, which is going to be safe based on the material selected, or we have to use different trial methods where the diameter of the spring wire will be considered, based on which we will reach a safe value of the induced stress. If we consider this spring constant or spring index, which is called C, this particular D will be eliminated with 1 degree of small d, because C is nothing but the ratio of capital D by small d. There is another aspect that is called material property, and which is the shear stress. Since we are considering the shear stress is having somewhat this particular value for the spring design. Now it's a standard value given by the association which deals with the spring design aspects. Earlier we used to have this value is equal to exactly half, but this value can be used for the yield stress, which is approximately equal to 0.3 times or 30% the yield strength of the given material. As far as the Indian standards are considered for the springs, they have suggested not to take 0.3, they have suggested to take 0.5 times the ultimate strength. So whenever the criteria are specified, we are going to take the value of shear stress equal to either 0.5 times this or 0.3 times the ultimate strength, and accordingly we are going to design the further part of our design aspect. Now before we conclude this topic, let us look at the important steps which are used for the designing of a helical spring. The very first thing is the estimation of delta based on the Pmax. In majority of the cases, we may have to use a formula or the empirical relation which is used to connect these two. If the value of Pmax is given, we can definitely estimate this value of delta, or if both the values are given, we can use them for the further steps. Second step, which is very common in almost all design, is the selection of material. Now the material will be either provided, or we have to select a proper material from the design data book based on the given application. Now when second part of the material selection is nothing but determining its shear strength. Now like we have discussed in the previous slide, we can design or we can select that based on Indian standard or based on the rough value of 0.3 or 30% of the ultimate strength. The next one is the assumption or finding of C. Now C can be found out using applications or based on the applications from design data book, or in most of the cases they are either assumed or they are generally provided. Now the standard value for the spring index is greater than 3. It should never be smaller than 3. That is what the suggested value is. The value may lie between 5 to 10, and generally values they are taken are between 8 to 10. So the values ahead of 5 are generally considered safe for index or spring index. The next is the determination of Wahl's factor. Wahl's factor K is already given in the formula, which is equal to using this formula we have to determine the Wahl's factor. The next thing is to find out the diameter or the wire diameter, which is small d. We already know this empirical relation. Once we are known about the safe value, Wahl's factor and all other indices, we can definitely find out the wire diameter. Now this is going to be the safe diameter because we have already considered the safe value of the shear strength. Then comes the determination of different specifications of a spring. The very first specification that comes afterwards is the mean coil diameter D, which is generally given by this particular relation, where this is the value of C, which is the spring index, into diameter small d. Then comes the number of active coils. Number of active coils are the coils which actually undergo the deformation, because the end coils are generally not movable. They are attached to certain surfaces or some application. So the active coils are the coils which lie between the ends of the coil, and that's why the active coils will be given by this particular empirical relation, where generally in case of the spring materials that we are going to use, the constant of rigidity will be somewhere equal to 81.4 gigapascal. The next thing is selection of end style. Like we have discussed 4 different ends. They are flat ends, flat plus ground ends, then there are square ends and square plus ground ends. So accordingly to total number of coils will change. Generally in that case the total number of coils will be equal to the small n, which are active coils, plus 1 or 2 number of coils, which are the end of the coils. Then comes the solid length. Now solid length also is given by the diameter into the actual or the total number of coils. This is the wire diameter. The next thing is the actual deflection delta. Now using the same formula of the delta which we have seen in the previous slide, the same formula we can use, and based on the new values of found out things, we can find out the actual deflection that this spring is going to undergo. There comes the total gap between the springs, and that is nothing but the total number of coils minus 1 into the gap between one of them. So gap is generally taken 0.5 to 2 millimeter. The standard value, if it is not provided, will take the average of that. The next thing comes out is the free length. Now the free length, as we know, is the summation of this particular terms, where this is the solid length, the actual deflection, and the total gap. Then comes the pitch, which is a very important parameter, and pitch will be given on or based on free length and the total number of coils minus 1, because we take the pitch between the two coils, so the end coil will not be considered. And the last thing is the spring rate or spring constant, which is also called constant of stiffness or stiffness value. That will be given by this particular empirical relation which we have seen in the derivation part of this particular design aspect. So these are what the steps that should be used for the procedure to design a helical spring, and certain formulae which are associated. Now students, you need not by heart this formulae, because you can find, or you can always find this formulae in the segment of springs in the book of design data book, PhD data book. So you need not by heart the values, rather you look at the steps which are carried out or the procedure which is carried out. So this was from my end about the design aspect. In the next session, we are going to solve few numerical based on the design of helical springs. Thank you so much for watching this video. If you like this video, please subscribe to Ekeeda. Thank you.